Um, Very good afternoon and welcome to the 17th lecture of the high pressure physics course. And in coming three lectures, I will be basically talking about solids under severe plastic deformations at high pressures and basically focusing on the plastic strain-induced phase transitions. So the topics that I will cover in coming three lectures will be basically first introduction to the plastic deformation, and then what are the processes that are involved in the plastic deformations, and then phase transitions at high pressure under severe plastic deformation, and the kinetic equation of plastic strain-induced phase transitions. Subsequently, I will talk about the experimental and computational methods for the study of plastic strain-induced phase transitions. Here, I will mostly emphasize on experimental part, as we do here mostly experiments, and I will also touch upon the computational methods. Some other researchers are experts for these computational methods. I will give references. And the last, I will talk about some recent advances in the study of plastic strain-induced phase transitions with some representative examples. So today's talk, I will mostly concentrate on the introduction to plastic deformation and the processes under plastic deformation. So here, there will not be discussion about the phase transitions under plastic deformation, but the basics of plastic deformations. So mainly, I will talk about the microscopic and the macroscopic pictures of plastic deformation, various deformation mechanisms, and then subsequently what happens under severe plastic deformation. So coming first to plastic deformation, and before I begin plastic deformation, let me revise once again the concept of stress and strain tensors that we discussed in initial lectures. So basically, when we want to deform a body, we have to apply some external force, and as an influence of this external force, some stress and strain tensor fields are developed in the material. So in general, you can define stress tensor as basically comprising of 9 components, where because of symmetry considerations, only 6 are independent components. That is these diagonal elements, and these off-diagonal elements correspond to shear stresses, and these diagonal elements correspond to the normal stresses. And the way it is presented is that there are 2 indices, I and j, where I first indices corresponds to the orientation of the surface on which the stress is applied, and other component corresponds to the direction of the force. And also, there is a strain field that is also developed in the material as a response to the external forces. And similar to the stress components, there are strain components. This is also a symmetric tensor. There are shear strains and there are normal strains. And these stress and strain tensors are related by elastic constants. So if you consider the harmonic approximation, where you can consider the Hooke's law, that is linear elasticity, you can relate this stress tensor to the strain tensor by some stiffness matrix, which contains basically all the elastic constants. And if you plot the stress strain curve, it will be a straight line. Whereas if you apply large strains, or you call it finite strains, then this linear elasticity is no more valid. And some nonlinear terms appear because the enharmonic components of the potentials start playing a role. And in this case, you cannot just define a linear relationship between the stress tensor and strain tensor. So you have to define higher order elastic constants, where basically these are the strain parameters and the internal energies under different thermodynamic conditions like adiabatic or isotherm. And if n is greater than 2, this corresponds to the elastic constants of higher orders. And if you plot the stress strain curve, it is non-linear, it is changing. So generally under high pressures, we deal with very large strains, and that's how we get non-linear plot between the pressure and volume. So that corresponds to the non-linear elasticity. But if you go on applying large stresses, if you go on basically subjecting material to large strains, the stresses does not evolve to very large values. So there are mechanisms by which finally these stresses are relaxed. So when this happens, we call it a plastic deformation. So if you plot the stress strain plot, up to a certain extent, it will follow linear elasticity, where harmonic potentials approximation is valid. And then beyond certain extent, it starts undergoing non-linear elasticity, where anharmonic components become active. But even in non-linear region, if you release the stresses, the system goes back to the initial strain state, that is zero strain state. Whereas if you reach certain stress level, that is called the yield strength of the material, and if you release the stresses, the strains are not zero. There is some remnant strain. So the region where your strain, there are remnant strain even after release of stress, we call it a plastic region. So here the plastic deformation has initiated. So this important parameter that comes out of this stress strain plot is the yield strength of the material. So of course it is a material dependent, and conventionally engineers define this yield strength as a stress where the stress strain offset is about 0.2%. So generally in elastic linear elasticity this is valid, whereas in case of non-linear elasticity it is difficult to define 0.2% of strain offset. So people define it 0.005 or basically 0.5%. These are by conventions. So generally, engineers do three different kind of stress measurements, stress strain measurements, in order to get the tensile stresses, tensile strength, compressive strength, or torsional strength, or the shear strength. So different kind of specimens are prepared from the bulk sample. For example, this kind of long specimen is prepared in order to study the tensile stresses. And when you apply stress up to certain region, it goes straight, and then plastic deformation starts. And then it reaches a maximum point where above which the stress basically reduces. And this is called the tensile strength of the sample. Actually, ideally, this curve should not come down, but this comes down because the way the stress has been defined. So this is defined, this is called the engineering stress, which is defined in terms of the initial configuration, like initial diameter of this. But as we know, if you do the tensile stress measurements, there is a necking. So actually, if in order to measure the true stress, one has to take the cross section of this neck portion. It's the smaller portion now. The diameter has reduced. So this has to be taken into account in order to measure the true stress. So if you plot the true stress, the same stress strain curve will be like this. So depending on stress measures, whatever you take, this tensile strength can occur at different strain conditions. Okay. The story is a little bit different in case of compressive strength measurement, because in this case there is necking and ultimate breaking of this. But in case of compressive stress measurements, there is no such thing. So basically, when you apply stress, it undergoes a plastic deformation certainly, but there is no such kind of behavior. So it goes on increasing, and in between, actually, there is some strengthening also happening under the plastic deformation, because the microstructure evolves, as we will discuss in later part of this talk. So when you release stress from certain stress condition and you unload it, there is some remnant stress, that is a plastic strain. This is still there. and whatever the elastic strain was there, that is recovered when you release the stresses. But when you increase or you reload the sample from this stress state, then it reaches yield strength which is higher than the yield strength of the initial sample. So this is a kind of strain hardening that happens in compressive stress. Okay. So these stress strain curves that I have shown earlier, they are not universal. Of course, they depend on strain rates as well as temperature. So if you go to higher and higher temperatures, the plastic deformation occurs at lower stress values. You can see here in this plot, for example, in aluminum, these plots corresponds to the measurements at 300 degrees centigrade, and this plot corresponds to the measurement at 600 degrees centigrade. You can clearly see that the plastic region starts appearing at very lower stress values here. So, but this is true for all materials. And if you apply large strain rate, so with strain rate, actually this yield strength increases. So the plastic region, you reach plastic region at higher stress values. So under shock compressions or under dynamic loading, you can reach higher yield strength states as compared to the static. So this is definitely a strain rate as well as temperature dependent. Now let us try to understand the macroscopic picture of plastic deformation. So in order to have a proper understanding of macroscopic plastic deformations, let me again talk about this general stress tensor. So as we know, in any matrix problem, we can find out eigenvalues. So in the same way, in case of stress tensor also, if you have a general stress state like this, which has all shear components as well as normal stress components, you can resolve, you can basically rotate or find out some coordinate system in which you don't have this off diagonal elements. So this is similar to the eigenvalue problem in quantum mechanics, and we can get the principal stress components. So you can get the principal stress component by solving this equation, where this is a general stress tensor, and this corresponds to the principal stress components, and this is a identity matrix. And you solve this equation, you can get the principal stresses. So this is important because in order to visualize this plastic deformation surface, or basically the criteria where material undergoes plastic deformation, this gives a simplified picture if we look in the principal stress space. So when you solve these equations, you can also find some invariants of this stress tensor. This J1, J2, J3, where J1 is basically sum of these diagonal elements. This actually is related to the pressure. And then this is another invariant, which basically is related to the shear stresses. And this is another invariant, which is related to the volume change. Okay, so these are the basically expression of these invariants under as described in terms of general stress tensor, and you can describe these invariants also in terms of the principal stress components. So now, before understanding this macroscopic plastic deformation surface, we need to first decompose this stress tensor in terms of deviatoric stresses and hydrostatic stresses. So it has been shown by Bridgman and other researchers that if you apply hydrostatic pressure, even you can go to very large pressure conditions without yielding of the sample. So for plastic deformation, one thing is important, that you need shear stresses or deviatoric stresses. So you need to decompose basically general stress tensor in terms of pressure and the deviatoric stress tensor. So this is how it can be decomposed. So pressure is basically a scalar quantity that is related to the trace of the stress tensor. And as we discussed, this is one of the invariant of stress tensor. And remaining part is the deviatoric stress tensor. So deviatoric stress tensor can also be expressed in terms of the principal stress components like this. Okay, now we need to define one principal stress space, because now we have resolved our stress state as three normal orthonormal, basically three normal stress components that are principal stress components. So we can define a space defined by these principal stress components. And any stress state will be basically a point in these principal stress space. Now, as we discussed, we can resolve any stress state in pressure and deviatoric stress part. So we can define basically, for example, consider this point P, which is some general stress state defined by three principal stress components, sigma 1, sigma 2, and sigma 3. And we can decompose this vector in basically two vectors. One is the diagonal vector, where sigma 1, sigma 2, and sigma 3 are equal at all the points on this diagonal direction. So basically, this line corresponds to the hydrostatic compression. So any stress state can be defined as sum of this hydrostatic stress state and plus this vector, which basically corresponds to the deviatoric stresses. So now we can have the projection. So this plane basically that contains this deviatoric stress tensor vector, this is called the deviatoric plane. Okay, so we can know about the deviatoric magnitude. Basically, by knowing the magnitude of this vector, we can know what is the magnitude of deviatoric stress, and also we can get the direction of the deviatoric stress in this plane. So different direction of deviatoric stress actually defines different kind of loading conditions. As you can see here, if I see in this map, if I basically project these three principal axes, principal directions of the principal stress components on this deviatoric plane, I will have basically these three lines on this deviatoric plane. And then my vector, deviatoric stress vector, will be basically some vector in some orientation, some direction. So now we can understand what different stress state means in this case. So as we discussed in this principal stress space, when all these principal stress components are equal, this corresponds to the hydrostatic compression, and that is the point on this diagonal direction. So in this plane, the hydrostatic pressure will be at the point here, at this origin. So your NP vector is 0 in that case, means the deviatoric stresses are 0 in that case. So this point defines hydrostatic pressure condition. And that's why from macroscopic picture, it looks like that under hydrostatic conditions, there will not be any plastic deformation, as there will not be any yielding of it. And you can consider other cases like uniaxial tension. For example, if you consider this sigma 1 as the direction of the tensile stresses or tensile load basically. So in that case, this sigma 1 will be larger than sigma 2 and sigma 3. These components will be equal. And if suppose it is uniaxial tension without any pressure, means the sigma 2 and sigma 3 will be 0. And if you see this angle, so this is the angle basically between one of the principal stress directions and the deviatoric deviatoric stress vector. Basically. So this theta basically defines the kind of stress environment you are giving to the sample. So under uniaxial loading, this deviatoric stress component will come along this way. So the theta will be 0 in that case. Whereas if you apply pure shear, so in case of principal stress components, the pure shear is given as the difference between this between these principal stress components, deviatoric stresses. So in this case, your sigma 1 minus sigma 2 will be equal to sigma 2 minus sigma 3. Of course, these components will not be same. So one component will be higher than the other two. And in this case, if you see the theta angle, it will be about 30 degrees. Whereas if you apply the uniaxial compression, in case of uniaxial compression, this will be similar to this case where your 1 and 2 components are equal and third component is slightly lower than this. Here, this corresponds to theta equal. Is there some problem in audio? Okay.
I think now it is okay. For a while it was, but now it is
okay. Okay. So, was the disturbance in this slide itself or in some different slide?
No, in this, when you were talking about pure shear, maybe you may like to redefine pure shear and uniaxial compression.
Okay. Okay, so basically what I was discussing about is the projection of basically stress state on this deviatoric plane. So if you see the projection of stress state on the deviatoric plane, pure hydrostatic will be basically on this point. So that corresponds to no yielding of the sample. That's why in hydrostatic compression experiments, you don't see yielding of sample. Whereas if you apply uniaxial tension, so one of the principal stress component will have higher magnitude as compared to other two, and this corresponds to theta equal to 0. And similarly, if you talk about the pure shear stress, you will have the sigma 1 minus sigma 2 will be equal to sigma 2 minus sigma 3, and basically this deviatoric stresses between the sigma 1 sigma 2 is equal to the deviatoric stress sigma 2 and sigma 3, and these components are not equal, and this corresponds to direction 30 degree, means theta is equal to 30 degree. Whereas if you consider the uniaxial compression state, in this case you can consider the sigma 1 and sigma 2 to be equal, and this is greater than the sigma 3, and this corresponds to theta equal to 60 degree. So any general stress state will basically, any general stress state in which there are deviatory components will basically represented by some vector in this plane. And this can be combination of tension, compression, or shear, or hydrostatic. So all these will be basically expressed by the deviatory vector in the deviatory plane. Okay, now let us consider what will be the yield surface. So, as we discussed, in case of principal stress space, where you have basically 3 orthogonal directions of principal stress components, you can consider a direction which corresponds to the equal magnitude of these components. So, this corresponds to the hydrostatic stress, basically. And then, as we discussed, the deviatoric stress plane, deviatoric space is basically some plane which is at some angle which is basically normal to this direction, and any vector in this plane corresponds to deviatoric stresses. So if your system is isotropic, then in any direction the yielding should happen at some value, some critical value of the magnitude of the deviatoric stress. So if you take the cross section of this pipe, basically you can consider that there is a cylinder which is there at the diagonal direction, and the diagonal direction represents the hydrostatic compression, and around this diagonal direction there is a surface which corresponds to the yield surface. So if your magnitude of stress reaches this surface, the material will start yielding, and it can reach in any direction. So it can be in this direction, or any direction basically. So if your sample is isotropic, in that case, if you see the cross section, it will be a circle. So your surface, which defines the yield condition, is a surface, and the criteria for this yield function, condition is basically when you have some yield function becomes equal to 0. So when your yield function is yield function is less than 0, yield function is basically some function of these different stress components. So when your yield function is less than 0, you are still in the elastic regime. Basically, you are inside this cylinder. So this is elastic regime. But as soon as this function reaches 0, you are at the yield surface. So unless your yield surface increases, you will be at the yield surface only, because the material will start relaxing stresses by moving on this yield surface. So there are some criteria defined for this yield surface. So first and foremost, what we consider that on this deviatoric plane, we don't consider any change in volume. So the volumetric plastic strain is 0. So we are talking about some condition, some pressure condition, and only talking about the deviatoric stresses. So the yield condition is considered to be independent of hydrostatic pressure. So you can be at any pressure, but at whatever pressure you are considering basically a cross section of this cylinder. So you are talking about the deviatoric stresses in order to define the plastic deformation. So there are some criteria which has been defined on this principal stress space or this deviatoric plane basically. These are Tresca criterion. In case of Tresca criterion, you basically define the yield surface as the surface at which the shear stress reaches some critical value. So this hexagon that you see here, that basically defines the Tresca. That is defined by the Tresca. So whatever is these basically difference in the deviatoric, the difference in the principal components of the stress tensor, they define your shear stresses. So whichever is maximum, you take that into account, and when it reaches some critical value, which is defined by this constant, then you reach the yield conditions. Whereas there is another criterion, which is called von Mises criteria. Both are generally very close and typically used by engineers. So in this case, you define the yield condition when second invariant of deviatoric stress tensor. So the invariant that we discussed, the J1, J2, J3, the second invariant, which is related to the shear stresses. So some function of this shear stresses, basically it is the root mean square of this, and this reaches some critical value that defines the von Mises criteria. So this circle that you see here, that basically defines the plastic deformation surface under the von Mises criteria. Of course, if you map these components in case of shear stresses, if you try to decompose these stresses in terms of shear stresses like sigma 2 minus sigma 3 and sigma 1 minus sigma 3, the same thing will deform like this. So again, here you can define a von Mises criteria, which corresponds to the yield surface, and a Tresca condition, which defines this. So this is the case when your sample is isotropic. But if in case of an isotropic sample, so you cannot arbitrarily take these directions of principal stresses. So it also depends on the directions of these principal stress components. So your yield function will not only depend on these principal stress components, but also the directions of these principal stress components in some reference frame, which defines the anisotropy of the system. So I will not go in much detail of these things because this is a subject in itself, and I would like to recommend to go through this reference. It's a book, nice book on continuum theory of plasticity by Khan and Moore. One can go through this book in order to have more details about the macroscopic picture and the continuum theory of plastic deformation. So now I will come to the atomic scale picture of the plastic deformation. So these macroscopic pictures basically take the yield strength as some parameter, material parameter, and it does not have any information about the actual atomic system, actual character of the material. So in actual system, how this plastic deformation happens. So one thing is that these deformations can happen even in perfect crystals also. When there are no imperfections, even in perfect crystals also this can happen, but one has to reach the theoretical yield strengths. So we will discuss later when we will talk about the mechanisms of plastic deformations. But mostly plastic deformations occur because of some imperfections in the solids. And so I will talk about the imperfections. What are the imperfections in solids? So let us consider first start with the point defects. So your atoms may not be in complete state, complete long state. There can be some vacancies, or some atoms of same type can be sitting at some interstitial positions. So these kind of defects are called point defects. So they also contribute to the plastic deformation, but these are important at high temperatures, where there can be diffusion of these defects. So there can be, similarly, there can be point defects corresponding to impurities. For example, if you have some different type of atom sitting at some place. So this means substitutional, if it is sitting at some lattice site, it is substitutional atomic impurity. Whereas if there is some different kind of atom which is sitting at the interstitial position, so it is an interstitial impurity. So this is also a kind of point defect. So these things affect plastic deformation when temperatures are high. Now come to the line defects. So in line defects, like dislocations are the main line defects basically. So there can be edge dislocation, there can be screw dislocation. So in order to understand edge dislocation, just consider a three-dimensional lattice, and you just insert one plane up to a certain extent. So in this case, what you see here, there will be some distortion in these unit cells. So if you basically try to make a loop, for example, if you are far away from this defect, then if you go with some magnitude in this direction and this direction and try to make a loop, all the vectors will be same. Whereas if there is some defect, then these lengths will not be equal. You need some additional vector in order to complete the loop. This vector is called Bajor's vector. And this kind of dislocation, this is a line defect. This kind of dislocation is called edge dislocation. So in 3 dimensions, if you see that there is a line that basically penetrates through the surface of this slide. So this kind of symbol represents the edge dislocation. And then there is another kind of dislocation, which is called screw dislocation. So there is a kind of twist in the lattice. So some atoms are sitting in this way, in this manner, such that there is a kind of twist. So there is one line here that goes through the sample, which corresponds to the dislocation line. In this case, in order to complete a loop, you have to go around some direction in order to make a loop. And here you have to have additional Bajor vector, this direction. In case of edge dislocation, your Bajor vector is basically perpendicular to your dislocation line. In case of screw dislocation, your Bajor vector is in the same direction as the dislocation line. So it is not always that there are only pure edge or screw dislocation. There could be mixed dislocation, which basically corresponds to both edge and screw dislocation. For example, in this illustration, you can see if you enter from this side, this basically shows there is a screw dislocation. But when you come out from this surface, here it is a edge dislocation. So this kind of dislocations are called mixed dislocation. If you take a plane, if you take the slice at this plane, what you will see, there will be slight atomic movements, basically this plane, that basically describes this mixed dislocation. So besides this linear or basically dislocations, the line defects, there are also surface defects, which could be grain boundaries, phase boundaries, twin boundaries, stacking faults. So your system is not entirely single crystal. There are different grains. Different grains may have different crystallographic structure as well as different orientations. So if there are different grains with some misorientations, the crystal structure is same, but there is misorientation. This kind of thing can happen at grain boundary. Otherwise, there can be phase boundaries also, like shown here in the TM image, as well as you can see here. These atoms basically have different structure as compared to this structure. So there can be grain boundaries, there can be phase boundaries, and then there can be twin boundaries. Twin boundary is basically a plane which has a mirror symmetry across this plane. As you can see, the crystal structure is same. Here and here it is same, but atoms are sitting in such a way that you have a mirror. So you can see it looks like that crystal is basically oriented in some other direction across this twin plane. So these kind of defect system. Other than this, there can be a stacking fault defects. So in general, in a crystalline system, we have some stacking sequence. Like in this case, in case of suppose FCC, you have ABC, ABC stackings. But if there is some movement of these atoms in some plane, you can have these stacking faults. So the sequence will not be same. There will be some problems in this. These are called the stacking faults. So these are also the defects which can contribute to the plastic deformations. So how we contribute to the plastic deformation? This is very clear from this cartoon. So when you apply shear stresses, for example, you consider this edge dislocation. So when you apply shear stresses, like here as shown here, when you apply shear stresses, so this basically atom, this edge, this dislocation line basically tries to slip in this direction. So this plane in which it slips is called a slip plane. So there will be some barrier defined by the atomic spacing called pulse barrier. It will have to face that much barrier. Basically, the shear stresses in this direction has to reach some critical value. Then only this slide can happen. So when it happens, then this plane basically moves this direction, and finally you get this state. So macroscopically, if you see, you will see a deformed system. So you will have the edge which is at some angle. But microscopically, when you see, these atoms, basically they have moved in such a way that they have relaxed this stress. So every dislocation will have some stress state, like here it is some compressive and here some tensile stresses are there. So they will be relaxed as you apply shear stress, and there is a plastic deformation. This is the mechanism we are studying. Same thing can happen to screw dislocations also. So if you have a screw dislocation and you apply this shear stresses in the same direction, then in this case, basically your dislocation line, like this is the dislocation line, it will move perpendicular to this. So it will move in this direction. This is the direction of motion of this dislocation line. Like in this case, here in case of edge dislocation, this dislocation line is moving in the direction of the shear stresses. Whereas in this case, it is moving perpendicular. But ultimate deformation that you get will be same when you apply the shear stresses. So these can be two different mechanisms in case of presence of edge dislocation or in case of presence of screw dislocation. But as I told, these movements are not same. Means it is not equally probable in all the directions. There are some specific directions in which these things can happen. So generally, these slip planes are the planes with highest atomic densities, and these slip direction in which this slip happens, they correspond to the nearest neighbors. For example, in this case, you see this FCC lattice. In FCC lattice, your highest atomic density is in this 111 plane. And in this 111 plane, you have nearest neighbor in this 110 direction. So if you consider a slip system, basically this slip plane and slip direction, they basically form the slip system of the crystalline system, whatever we are considering. So in this case, we have some slip systems, which is defined by this 111 plane and 110 direction. So in the same manner as FCC, there can be different slip systems with different crystalline system. For example, BCC will have different slip planes. For HCB, we will have different slip planes. So these the shear stresses that you apply, so they will basically, there has to be some component of shear stresses in these directions in order to facilitate activation of these slip systems. So if you want to deform your system in some arbitrary direction, it will be basically a mixture of activation of several slip systems. So it is not just one slip system which is activated under a general plastic deformation. One needs to basically activate several slip systems in order to reach the desired plastic deformation. So here is the list of different slip systems in different crystalline systems, like in FCC, and BCC, and hexagonal. In FCC, you have 12 slip systems, as I discussed. Highest density is in 111 plane, and the slip direction is 110. So in the same manner, in case of body center, there are different planes, which are the slip system, basically highest density planes. So overall, if you add up all these things, there are about 48 slip systems in case of body center. In case of hexagonal closed peg structure, so there are three types of slip systems. One corresponds to the basal plane, one corresponds to the prismatic plane, one pyramidal plane. So there are 6 possible directions in which it can happen in pyramidal plane, 3 possible directions in case of prismatic plane, in case of 3 possible directions in case of basal. So these are the slip systems in these different dislocated systems. So when for general plastic deformation, combination of these systems has to be activated in order to have the desired plastic deformation. Okay, having said that, as we discussed, these are the imperfections that are responsible for plastic deformations. But it is not that there is a certain number of these defects. So initially your system may have some density of these defects, but it does not mean that it will be that much. So there can be a generation of dislocations. There can be generation of defects while when you are subjecting to shear stresses. For example, there is a Frank Reed loop source. So when you have a dislocation line, and suppose it is anchored at this B and C points. So when you apply these shear stresses in this direction, these points actually will not, the dislocation movement will not happen at these points. So in this case, your dislocation line will basically be stored. And then as you go on applying these shear stresses, this eventually becomes like a loop. So this is how it evolves. So this line is bent like this, becomes circular, then it is bent like this kind of structure. And then finally it reaches some value when this is a loop in itself. So this is a dislocation loop that is generated by the Frank source. And again, in the center, you will have again this dislocation. So as you go on further, applying more shear, again, some more dislocation loop will be generated. So you will see here, as you go on applying shear, these loops go on. So your dislocation generation happens also under plastic deformation, and that can further contribute to plastic deformation. So other mechanism of plastic deformation is twinning. For example, you consider this line system and you apply some shear stress. So in this case, instead of slip, there can be a region, basically a band, in which the atomic movement happens in such a way that a twin plane arises. So this system, this open circles are the atoms basically which have not moved, and this closed circles, this filled circles, they correspond to the atom which has moved from their position. So this atom has moved from this to this position, yes, and you have a line system basically in between these two structures, in these two orientations. So this is a twin plane which has a mirror symmetry. Basically, if you see these atoms, these are the final atomic positions. So these atoms basically means that there is some mirror symmetry at this point. So similarly, there will be also a mirror symmetry at this point. So this is a band basically which arises because of it. So when you apply shear stresses, if your plastic deformation is through slip planes, it will be deforming like this. Whereas if it is through twin planes, it will be deforming like this. So these things can also happen to facilitate the plastic deformation. But of course, this twin actually contributes very little to plastic deformation. And generally, it is more important at low temperatures. Okay, now coming to the deformation mechanism. So as we discussed, the atomistic picture of different ways in which the material can get deformed. Now it is kind of summary. So what are the different possibilities of this plastic deformations? So there is a very nice article by M.F. Ashby, and he basically classified all these mechanisms in six parts. Basically. So one is the defectless flow. As I discussed initially, when even in the perfect crystal, when you apply shear stresses, it cannot withstand infinitely large shear strengths. So there is some finite shear strength, so which is called theoretical shear strength of the sun. So if your shear stresses exceed this theoretical shear strength, then you will have plastic deformation. So this is a way in which the material can undergo plastic deformation, which is defectless flow. So other than this way of deformation, all other deformation methods have basically they depend on the defect concentration. So they depend on defects. So other mechanism that is actually the main main mechanism of plastic deformation is the glide motion or slip, basically slip of this dislocation. So glide motion of dislocations. So this happens at low temperatures, and this go on occurring, and it is limited only by the presence of obstacles to the slip, like there can be boundaries or impurity solutes, other dislocations. So this is the main mechanism by which a material undergoes plastic deformation. So other than, so generally this is a low temperature process. At higher temperatures, there is also a possibility of dislocation climb. So as we discussed in the previous slides, there is a dislocation slide. The dislocation line basically slides along in some plane, slip plane. But sometimes at higher temperatures, because of the diffusion control process, there can be dislocation climb also. So this dislocation line can move up. So if I go to the dislocation picture, this cartoon which shows the dislocation. So here, this dislocation line is basically moving in this slip plane. This is what is called dislocation line. Whereas if at high temperatures, this can move to this position or some higher positions. So this is called dislocation climb. So this is also a mechanism of plastic deformation. And this is important at high temperatures, where the diffusion starts playing. And then, as I discussed, these point defects also contribute to the plastic flow. So there are two kinds of plastic flow depending on the point defects. One is called the Navarro-Herring creep or plastic flow because of these point defects is basically a bulk diffusion, where the bulk diffusion happens. Whereas there can be point defect diffusion only in the boundary, the diffusion at the boundaries. This is called the Koebel creep. So this happens at relatively lower temperatures. This happens at relatively higher temperatures. So these also contribute to the deformation of plastic deformation. And as we discussed, the screening also is one of the way in which plastic deformation can happen. But of course, its contribution to the plastic deformation is very little. So main component main mechanism which describes the plastic deformation is glide motion of the dislocations. And the tuning also happens, but it is mainly important at low temperatures. Or this can happen at high strain rates, for example, under shock loading. So based on different energies which are required for activation of this defect mechanism, this plastic deformation mechanisms, Ashby has actually generated some deformation maps. So these deformation maps are in temperature versus normalized stress space, as well as it can be in the strain rate and this normalized stress. So you can see, like in this plot, in this map. So basically from these maps, one can know what kind of deformation mechanism will be important under the given process of plastic deformation. So you see here, this axis is basically homologous temperature, which is basically temperature divided by the melting temperature. And this is the normalized tensile stress. So which is the stress divided by the shear strength. So in this case, you see at low temperatures and at lower stresses, these dislocation glides are not yet active. So this is still an elastic region. But in this case, even there are small stresses are there. So diffusion can still happen. And this will be Koebel diffusion at low temperatures. And in case of higher temperatures, it will be Navarro. But if you go to very high stresses, high shear stresses, then in that case, dislocation glide is the dominant player, which basically decides this plastic deformation. And in between, at higher temperature and higher stress, you have dislocation creep also that occurs, and which leads to the plastic. In case of strain rate versus normalized shear stress map, you can see here also there are different mechanisms in which plastic deformation happens in different regions. So these maps are very helpful in basically describing the way deformation happens in different systems under different strain rates and different temperature conditions. So it can also be mapped in three-dimensional space. So where one axis corresponds to your strain rate, one axis corresponds to your normalized stress, one axis corresponds to homologous temperature. Here also you can see different region corresponds to different way in which plastic deformation happens. And this region basically corresponds to the dislocation glide. So you can see the dislocation glide is important at very low strain rates also and at lower temperature. So mostly the quasi-static experiments on a plastic deformation, these will be the dominant player in the plastic deformation. And further in future lectures, when I will talk about the plastic strain-induced phase transitions, basically we will try to explain the phase transition basically which is facilitated by the dislocation glides. and dislocation pile-ups at the grain point. We will discuss in subsequent lectures. So this was about the deformation maps. Now I will talk a little bit about the severe plastic deformation. So mainly when there are large plastic strains and which involves complex stress states, very high shear stress, which results in the high defect density, and it makes ultra fine grains, size of nanocrystalline structures. Then we basically reach the plastic deformation, severe plastic deformation. So initially, when you apply plastic deformation, there will be dislocation glides. There will be dislocation glides within the grains. But eventually, when you go on further applying shear stresses, the material can undergo severe plastic deformation. So there will be grain refinement, there will be grain rotation. That happens under severe plastic deformation. And basically, this is the region of plastic deformation that is of interest when you want to study the plastic strain into expansions. So here I have just listed what happens the grain refinement process. So first, dislocations, which are initially distributed throughout the grains, they actually rearrange, group together into dislocation cells, and this actually reduces the total strain energy. And then as deformation continues, further apply higher shear stresses, the more dislocations are generated, the misorientations develop between the cells, and then subgrains are formed. And this is how the grain refinement happens. The process repeats within the subgrains until the size becomes sufficiently small such that the subgrains can rotate. And then the grains can also rotate. So this is the way how the grain refinement happens under severe plastic deformation. So your material basically reaches some kind of saturated hardness state, and it becomes independent of the history or the pathway in which the plastic deformation has been applied. So this is the region of plastic deformation that is of interest for the study of plastic strain-induced phase transitions. So there are different methods in which the severe plastic deformation can be achieved. So one thing is the high pressure torsion. So this is basically the main way in which we study these plastic strain-induced phase transitions. So here you basically put sample in between two anvils and you apply torsion. You basically rotate one anvil with respect to another when the anvils are under some load conditions. So this is the high pressure torsion. So I will talk in detail about this high pressure torsion in subsequent lectures. Other than this high pressure torsion, there are other methods which are important from engineering point of view, material forming and forging. So like equal channel, angular pressing, accumulative roll bonding, twist extrusions, multi-directional forging, continuous severe plastic deformation method, surface severe plastic deformation method. And actually, we will not talk about all these methods of severe plastic deformation. We are interested in phase transitions under high pressures under severe plastic deformation. So mainly we will be focusing on the high pressure torsion experiments. And in order to go through in detail about these different methods of severe plastic deformation, I would like to recommend this recent review article by Pandey. And with this, I have reached the end of my presentation or my lecture today. Now we are open for questions.
After the talk is closed, let me talk to you for a while.
Okay. I think there are no questions in chat box as well as on the webex, so we may close the talk. Is it closed now? Yes, sir. Now we can.
The comment which I want to make is what you have covered today is quite